In this hopper assignment, you're going to draw and dimension two flat pieces of plate that are going to be welded together to make this hopper. And this is an exercise in thinking about how flat pattern shapes can be different from finished or formed shapes. What you are looking at here in this first slide is the top, front, and side view of a hopper that has been welded together. And this isometric view in the upper corner is what the thing looks like. It doesn't have it's open at the back end. I just made it a three-sided thing. And you're looking straight down on the top, so this top view is foreshortened. Then here in the front view, you are looking straight towards the front, so this view is foreshortened. And then in the end view, you are looking towards the end of the hopper, so this view is foreshortened. So let us think about how can we figure out what size and shape to make these three pieces of plate so that they will weld together correctly. And who is your customer for this drawing that you would make? You have an internal customer, probably the shear operator in your shop, or maybe somebody on I don't know, some other kind of machine, a burn table or something. And you're going to give them a dimensioned drawing so that they can make pieces of plate that when you tip them up at these angles, they will come together and can be welded and make the right size hopper. And this is the hopper that you want. Here's the inside length of the thing, and you want the front end plate to sit at a 45-degree angle. Here in the end view, here's the width across the hopper at the top and at the bottom, and you want the sides of the hopper to be sitting at a 56-degree angle. And when the thing is all welded up, you want it to have a finished height of 36. But of course, these pieces of metal are going to be much higher than 36 because they're all foreshortened in these views. Okay, so let's think about how you would find some dimensions. Well, and right here we're looking at the formed view, the front view. So we're given that the inside length is 120 inches. So that length probably remains. That will be 120 inches whether it's tipped or lying flat. What about this bottom length? When the thing is welded together, it appears that this front end forms a 45-degree angle with the ground. So can we use that to figure out how long this bottom length should be? And yes, we can. If we make a triangle that represents this thing when these sides are tilted and they're welded together, this top corner of the hopper will be 36 inches above the ground, and this front surface will be 45 degrees above the ground. So whatever the sizes are, this bottom edge here is represented by this phantom line bottom edge at the bottom of the slide. So can you figure out if you have a 45-degree triangle that's 36 on one side, how big is it on the other side? Oh, 36 over here. It's probably 36 over here too, isn't it? So this edge is 36. The overall length is 120 inches. What is 120 minus 36? That should give you that bottom length of that thing. But we don't know how high it is. So now let's think about how high to tell our shear operator to cut it. Now let us look straight on at the end view of this finished hopper. And when we look at the end view, this dimension tells us that these two big old long side pieces are supposed to be tipped up at a 56-degree angle above horizontal. Okay, so if the finished hopper is 36 inches high and the finished hopper has a side that's tipped up at a 56-degree angle, this heavy line that I've colored in here in the end view, that is actually the edge view of that big long side when it's tipped up. You're looking at the edge right there. How high is that edge? Well, may I suggest that you could draw yourself a triangle. And this triangle is essentially this edge of the hopper. The height of this thing is 36 inches above the ground. The angle that the hopper side is tipped at is 56 degrees. That tells you that looking at this triangle, it's the hypotenuse of that triangle that will be the height of your flat piece of metal that they're going to weld together. So whatever length you get for this hypotenuse, that is the actual height of this flat piece of plate when it's lying flat on a table. Now let's think about the end piece in the hopper, and up here in the upper corner we're looking down, we're looking at a top view of the thing. So how big is item 2, the end piece? Well, they already tell us that it's 72 inches corner to corner, so we got that. And they do tell us as a reference that it's 23 7/16 corner to corner at the bottom of the thing. So we just have to figure out how high is that thing. Now, if you look straight on at a side view, at the front view of the hopper, and that's what we have here on the left side of our slide. This partial hopper is the front view of the hopper. The end plate that we are thinking about is supposed to be sitting at a 45-degree angle when it's welded up. And when it is sitting at a 45-degree angle, that top corner will be 36 inches above the ground. So if it's 36 inches above the ground, when it's sitting at a 45-degree angle, how long is the hypotenuse of this triangle? Whatever that hypotenuse length is, that is actually the height of your flat piece of end plate when it's lying on the table. So, I hope that wasn't too confusing. Now, when you get your two flat patterns drawn out, you'll draw and dimension this front piece, and there are going to be two of those, but you'll just draw and dimension one of them. And remember, it's not 36 inches high, it's higher than that. And you'll draw and dimension this end piece, and remember, it's not 36 inches high either, it's higher than that. These two pieces, when they're lying down flat, are going to be different heights. But how you can check your work is, if you think about it, the two of them have to weld together corner to corner at this valley angle. And because they weld together corner to corner, however long this edge of your side piece is, has to be the same length as however long this edge is of your end piece. Now these pieces are different heights and different widths, but these two slopey lines have to be the same length so the thing can weld together. So that is a way to check your work and see did you get them right. Please holler if this seems confusing to you. And then you don't have to answer this question. I'm just throwing this out there. What would the valley angle be if you have let me back up. This angle is 45 degrees above the ground, and this angle is 56 degrees above the ground. What is the actual valley angle in the corner? It's not 45 and it's not 56. Now, if you are using Inventor or SolidWorks, you can just ask it and it will tell you. But if you use that old-timey valley angle chart that we looked at in the last lecture, you will discover that this angle is about 40.5 degrees above horizontal. So considerably flatter than either 45 or 56. It's surprisingly flat. So that's interesting. Anyhow, holler if you have trouble figuring out what we're doing in this one.